Really excited to have the latest Dean's Invited Speaker Series talk. This is an effort by Yale Engineering to reach out to members of our broader community that are engaged in industry and in other impactful work in the world, to bring them back to campus, have them tell us a little bit about what they're doing, make some connections with all of you, so that you can sort of see firsthand the impact that Yale Engineering is having. So today's speaker, I've really enjoyed getting to know. His name is Wen Chen. He's a Chief Technology Officer at AP Memory, which is a company that designs memory for CS and AI systems. He's got a lot to tell us, and I'm very excited to have him speak. The format for this will be he'll give about a half hour or so of prepared remarks, and then we'll have some Q&A. So I have the honor of asking the first few questions, which I will enjoy, and then I'll hand it over to you guys. So be thinking about what you want to ask. And then be sure to hang around afterward. We have some nice refreshments, and he's a very photogenic guest, so you may want to take some selfies and things like that. So without further ado, we'd like to welcome Wen Chen to speak to us.
Thank you, Dean Brock, for the introduction. Good afternoon, everyone. It's a great honor to be here. I kind of chose a big title, Challenges and Opportunities in High-Performance Computing. This was something that I presented to a forum called Taiwan Semiconductor Day in Japan last year. It was really meant to be semiconductor, so I didn't even put it in the title. I'm going to talk about high-performance computing in the context of semiconductor technology. But before that, a little bit about myself. I came to Yale in 1988. When I came here, Reagan was still the president. Soviet Union was still around. But more importantly, U.S.-China relationship was good back then. So as part of that U.S.-China relationship, there was a program called CUSPIA, China-U.S. Physics Examination and Application. It was a program started by Professor T.D. Lee at Columbia, and I was part of that program. I came to Yale to study applied physics. For various reasons, I ended up working for Professor Ma. It was one of the best things that ever happened to me. I did my PhD with Professor Ma, as you can tell from the title, in CMOS technology. After I graduated from Yale, I went to Intel. Most of Professor Ma's students went to IBM. But back then, IBM was in a little bit of trouble, so we went off to West Coast. I spent about 9 years there. I started with device engineering. That was my PhD area. Went into design, in particular CPU design, product design. And I came back to technology area. I did some SRAM development, technology planning. So I covered a bunch of wide areas. By about 2001, dot-com bubble came and went. I figured that I should exercise some of the what I call judgments that I developed, that I wanted to do something on my own. And I went off to do some startups. I did a few startups in memory, high-speed interface, and some other more peripheral areas. But my main area remains memory. So in 2011, I started this company called AP Memory. On next page, I'm going to talk about AP Memory. But currently, I'm chairman CEO, but my main function is CTO of this company. A little bit about AP Memory. We started in 2011 in Taiwan. Our team actually had been tinkering around for a number of years in the US. We went public in 2016 in Taiwan. We've been public since then. We mainly play in three areas. One is IoT. In IoT, what we do is we do extremely low power memory. And in this area, in IoT memory, we don't have a precise number, but we think we have much larger than half of the market share. We probably have close to 80-90% market share. The second area is AI high-performance computing. This is what we're going to talk about today. Here, what we do is extremely high bandwidth memory. This is different from HBM that you hear about, and that's what we're going to get into next. And in terms of industry impact, this is still emerging. And the third area is in advanced packaging, somewhat related to the second area, but more specifically, we provide silicon capacitors, passive devices for advanced packaging. We customize devices so that we can support the advanced packaging better. In some ways, we think of capacitors, memory is obviously storage, right? Storage of information. Capacitors are also for storage. It's storage of energy. In that sense, we're kind of doing the same thing. Before I get started with my talk, I wanted to spend a couple minutes talking about Professor Ma. Professor Ma is one of the best persons, or one of the most important persons in my life. I studied with him for 3.5, about 4 years. He, being a foreign student himself, he really understood what I needed. And this page is the first page of my thesis after he revised it. And it's embarrassing. I don't want you to read it because it's too embarrassing. But I take some comfort in having shown him this page on his 70th birthday, just about 10 years ago. In this talk, I mainly want to talk about what I call, or maybe I shouldn't say what I call, the two dark clouds over high-performance computing. It's obviously very, very hot, but there are two fundamental limits to high-performance computing. One is memory bandwidth limit. The other is energy bandwidth limit, which is power delivery. And we can talk about some of the opportunities. AI is all over the place. Everybody we talk to talks about AI. And I kind of picked 2 data points to show how big it is. On the left, we have the model size of these AI models growing about 10 times a year. There are very few things in life that grow 10 times a year. Maybe bacterial growth or something. In semiconductor, we have Moore's law. Moore's law grows about twice every 1.5 years, or roughly 10 times every 5 years. The difference between 10 times every 5 years and 10 times every 1 year is not 5x, but a power of 5. So this is very, very powerful. And if you were to take this further, extrapolate this out, let's say today we have enough memory to build 10 million machines for AI. If this were to continue, in 7 years, you have enough memory to build 1 machine. And of course, we want that to be built in New Haven. So that's how powerful this growth curve is. And on the right, it's the economic impact. This is the market cap of NVIDIA. Right now, we are looking at NVIDIA between France and Italy, just after G7, about 10% of the US GDP. If this were to grow another 10x, NVIDIA will be the same size as United States GDP. So that's the size of the impact that we are talking about here. In the year 1900, a physicist called Lord Kelvin, I'm sure you guys know, said in a speech that in classical physics was doing very well. They almost understood everything, except for 2 dark clouds. And I don't know I don't know enough to describe those 2 dark clouds very specifically, but those 2 dark clouds were resolved by quantum mechanics and relativity. And I draw a parallel here in high-performance computing. Even though it's very hot, obviously it has very high impact, we suffer from 2 fundamental limits, which is energy bandwidth limit, memory bandwidth limit, and energy bandwidth limit. I'll get into that. This is a chart that shows the performance improvement over time. This spans roughly 20-something years. Actually, this could go back 50 years. It's the same trend. So the upper curve is the computing curve. It obviously has been, the lower curve is the memory and the connectivity curve. It has been moving much, much faster than the lower curve. And since CC wave was here, CC wave was on the upper curve, and I, unfortunately, have been on this curve, and it shows how important it is to get on the right curve. So you might say, this gap has been there for so many years. Why is it such a big deal today? It's such a big deal today because CPU can deal with this kind of memory performance or low performance of memory, but AI cannot. CPU, if you guys remember the von Neumann model, you fetch some data from memory, do something, and write it back. That's all you do. And the amount of memory that you can read and write is fairly limited by that mechanism. But AI, let me kind of present a overly, maybe unfairly simplistic model of what AI does. AI, well, today's AI, neural network computing, is basically this formula here, B equals W times A. A represents the input vector in some form. B equals it represents the output vector. And there is a huge set of numbers. We call it weights. And the size of that weight matrix depends on what you want to do. But it can be very, very large, like I showed on the first page. When you have this kind of computing, every time you do anything, you need to read the weights. And for that reason, the performance of an AI system, if I were to write it out as a formula, we often describe the AI system performance in number of flops, which is the number of flops per second, And that, in fact, is a multiplication of two factors. One is how many flops can you do with a unit amount of data, or number of flops per byte, and the other is the number of bytes per second that you can fetch from the memory. And the second term here is memory bandwidth. So memory bandwidth is directly, other things being equal, is directly proportional to performance that you have. So without this memory bandwidth improving logic doesn't help you very much. For that reason, the gap between computing and memory performance is a big deal for AI. Today, if you were to look at any of the state-of-the-art systems today in AI, what you will find is a memory called HBM, high bandwidth memory. It's already sounding very impressive. What it does is it's obviously higher performance or higher bandwidth memory relative to the traditional memory. The traditional DRAM has something like 16 pins, graphical maybe 32 pins. But HBM has an impressive 1,024 pins. And the reason it needs that many pins is to do higher bandwidth. So here, this is very good. This has been doing all the GPUs, and we heavily rely on it. But it has a limitation. The number of wires that you have limits the bandwidth you can achieve. And the length of the wire determines the minimum energy you have to spend, regardless of the circuit that you can design. So for that reason, this system has its own fundamental limit. Obviously, you could increase the number of wires, but given the space that you have, there's a physical limit to the number of wires you increase without running into performance issues. So the solution from here, just topologically, obviously, is to put the memory directly on logic. By putting memory directly on logic, instead of having 1,000 pins with the same kind of density, you could have 1,000,000 pins, because it's two-dimensional. And this is what AP Memory has been doing for the last 6 years or so. We have a trade name called VHM, very high bandwidth memory. How inventive. So that's what we've been doing. Once again, back to the state-of-the-art GPU. So this presentation was made last year, so this is the state-of-the-art. I think they have better things than this. But the story doesn't change. In terms of memory connection, it's edge-to-edge or lateral. If in the second picture on the left, you can see the SoC, which is the computing chip, and the memory are connected laterally through what's called an interposer. The number of connections and the length of the connections limit your bandwidth and energy. And there's another thing. When you think of how this chip is powered up, the power supply chips are on the sides, on the edges. So you can see power actually comes in from outside of the chip laterally through the PCB to the chip. And this is what I call the energy bandwidth problem. Because here, once again, you have a two-dimensional space trying to deliver energy laterally. And here I try to estimate the magnitude of the problem in the two-dimensional power delivery case. And here I pick a case where we have 1,000 watts. This is actually already outdated because I've seen chips being planned for 2,000 watts or maybe 3,000 watts. The SoC, or the main chip power supply, is on the order of 0.6 volts. So simple math, 1,000 divided by 0.6, 1,600 amps. Right? So Ohm's law, delta V is I equals R. So if I take 1,600 amps and I put just 0.1 milliohms, it's very small, very difficult to achieve this kind of resistivity. I get something like 0.16 volts. Given the power supply of 0.6 volts, dropping 0.16 is already something like 30%. It's totally unacceptable. So this is already a big problem. But on the other hand, if I were to try to achieve 0.1 milliohms with copper resistivity is about 1.7 e minus 8. To do 1 square of copper and achieve 0.1 milliohms. Obviously, in a chip, you need much more than 1 square to get to supply your chip. Let's say you could do it one square. You need something like 170 microns of thickness of that copper to achieve 0.1 ohms. So you can see with this kind of power supply scheme, you have already run out of steam in terms of supplying higher power. Today, what people do is they jack up the voltage and let it drop. Right? So obviously, so let's say the power supply is 0.6 volts, they give it 0.9 and let it drop 0.3. And that's a total waste of power because you're not only, you're burning power everywhere just to get to the 0.6 volts at the main chip. But the third dimension has always been there. In fact, one of the things that we already do in these chips is three-dimensional, which is cooling. So when you have a chip like this, there is usually a heatsink on top. The heatsink is going to take the heat from the chip in the third dimension off of the heatsink. And in fact, this heatsink now this whole package now can go into water, can go into immersion liquid. You can almost think of it as four-dimensional because not only is the heat coming off in the z dimension, it's also coming off of all three dimensions in the cooling liquid. So this kind of the third dimension of cooling has to be applied to memory and memory bandwidth and power bandwidth in order for these bottlenecks to be solved. Some of the things that we have done in the past few years, this is one example. What we have done is, having realized this problem, we started in 2018 trying to experiment with bonding a memory wafer to a logic wafer. This is what I was talking about in 3D. So we take a DRAM wafer, a memory wafer, and a SoC wafer, a logic wafer, and we bond them face to face. So this is kind of a cross-section of what it looks like. So the logic wafer being on top and DRAM wafer being on the bottom, you could make connections at a pitch of something like a couple microns. So every couple microns, you can have a connection. So you can imagine within a couple square millimeters, you can have 1 million connections, theoretically. So the number of connections is totally not a limitation here. And after you bond, if you can imagine the two wafers being bonded face to face, now you have backside on both sides. Right? So you need to grind down one of the wafers and drill what's called TSV, or through silicon vias, to make connections. And this technology, in fact, has been used in image sensors for a long time. So this technology itself is not new, but we applied it to DRAM and logic wafers. And we were able to make a chip starting in 2018, but we finally went into production in 2021 with this kind of setup. Once you bond the two wafers, they actually look like one wafer. This is a remarkable thing. You almost can't tell that it's two wafers combined. So theoretically, you could have multiple wafers combined. And this is one of the one of the ways of measuring what we have done. So this is this chip that we made was for an algorithm called Ethereum mining. It's a cryptocurrency mining. It happens to be an algorithm that uses heavily memory bandwidth, just like AI, or very close to AI. And with that algorithm, what we have here is 3 state-of-the-art GPUs. These are like 7 nanometer, 6 nanometer GPUs, compared to our ASIC, which is made with relatively old technology. We have about 10x performance enhancement because of the higher bandwidth. At the same time, the power, watts per mega hash, which is the power that you consume, drops by a factor of 2 or 3. And the reason it didn't drop as much is because the logic is older technology and it consumes more power. In terms of memory power is actually much lower by a factor of 10 or so. And this is one of the first demonstrations of 3D integrating logic and memory and seeing its benefits. So we envision this kind of system where you have a chip, you have logic chip, SoC, you have memory, possibly multiple layers of memory, directly on top. Below that, you could have some I/O die or whatever peripheral logic that you want to support, and right below that is power supply. So these power supply chips will supply the low voltage domain vertically, directly to the SoC and to the memory. So the entire system will be, the energy flow will go from the bottom up and vertically in Z direction, and memory bandwidth as well in Z direction. You might ask, you still have to somehow get energy from the outside, right? So this is where, if you think of how power supply is delivered today, what's delivered to our house is 110. But what's delivered to the power station is 110K or something, or higher voltage, 300K or something. So you could deliver a higher voltage into these power supply modules and deliver a low voltage out, and thus reducing the current in the lateral dimension. And this is what we envision as the 3-dimensional high-performance computing package or chip. So this is some of the implications that we see in terms of this technology. So in semiconductor technologies, this talk was to a semiconductor audience. In semiconductor technology, you really have 2 dimensions of improving performance going forward. One is continue to scale. You can go from 5 to 3 to 2. There are many nodes that you can go. The amount of investment that you need to make for that kind of scaling is exponential. Right? It's once it's exponential, just like the market cap of NVIDIA, you can very quickly reach the GDP of the US. Right? So you may have a hard limit somewhere, and we don't know where. It could be very close, it could be very far. But this is certainly one direction, and this is the direction that the most of the policymakers are looking at. How do we get an advanced packaging or advanced node fab into our country? There is another dimension, which is to figure out how to package the existing silicon better in such a way that you get 3D benefits of memory bandwidth and energy bandwidth. And in some of the countries or companies where this direction is not an option, and we can think of many, including the US perhaps, this is less of a more difficult option. This is actually a direction where CapEx is less, possibly the performance gain is more, and you may have more flexibility in terms of combining whatever technology you have. But of course, the most likely scenario is the industry is going to go both directions. Right? And it remains to be seen how far we can go in scaling and how much of the 3D investment people make in terms of performance enhancement. So this is actually my last page. So I'm happy to take any questions you guys have.
Good. Well, let's bring over the chairs.
Sure.
The only thing we lack is a fire. But It's probably for the best. Okay. Well, thank you so much, Wen, for the presentation. I'm really curious about how, we've been focused a lot on the advent of AI here and what it's doing to, our daily lives. And we spoke a little bit earlier about how AI tools are impacting the way your design process works. Is it actually having an impact, or do you think it's sort of still too early to see genuine improvements in terms of efficiency or answering these kinds of questions using AI technology?
There are plenty of people trying. I think it's obvious that it has a huge opportunity in terms of making improvements. We're not seeing a major impact yet. We use commercial tools. When the tools improve, we improve. And so right now, we're not seeing too much of it yet, but I'm sure it's coming.
Mm-hmm. And if you were to give or proffer any advice to our students that are interested in getting into electrical engineering or other fields that might have some sort of bearing on the future directions in this area, would you tell them to kind of stick to the basics or to, sort of get fully up to speed with AI tools and technology?
It's actually both, I think. So the basics, things come and go. Right? So today it's AI. 20 years ago it was the internet. But does it really change how we look at study and how we look at degree programs and career path? I don't think so. I think in the end, we deal with humans. Mm-hmm. Technology is just a tool. So fundamentals are still very important, but learning the new tools, obviously nobody will survive without accessing the internet today. So you have to learn how to use it, but that won't replace the fundamentals that we have to learn.
Mm-hmm. Math in particular, right?
Math in particular, yes.
Good. Just checking.
Yes.
Right? Yeah. I got a nice math lecture from Wen's son earlier today, so that was very enjoyable for me personally. I guess zooming out a little bit in terms of your career and your development, I think there's always this moment where when you're thinking about doing a startup or something like this, where there's a kind of a leap of faith or a moment of risk that feels almost like too much. What was it that led you to taking that leap, the first leap when you first started your first company?
That's an interesting question. I worked for Intel for about 9 years, and those were Intel's best 9 years. So I was somewhat financially secure because of that, and that was one of the factors, to be honest. But more importantly, I felt like I had done enough things within a big company environment that I've developed my own judgment as to what works in the market and what works, technically. I wanted to exercise those judgments, even though I actually didn't know what I would do when I left Intel. So I went off and explored some areas. I found a market opportunity that I thought was feasible. Mm-hmm. I started doing it. There you go. So it's hard to say what one element drove that, but I think the desire to exercise my own judgment was probably the key.
Mm-hmm. And how much did the network you had developed from your years at Intel, how important was that in terms of actually moving forward? Did you draw on it, or were you just kind of off on your own?
I was kind of off on my own. Mm-hmm. So back then Intel was a very closed, especially in technology development, it was a very closed system. I rarely went to conferences. It was like working for the CIA in some ways. So you don't really talk to anyone. Uh-huh. So Intel was different back then. So when I went off to do my own thing, I was pretty much on my own.
Did you call up TP and ask him for any advice?
I probably did, but I forgot what he told me. He probably told me not to leave Intel.
Yeah, okay. Yeah. And I guess maybe a follow-on question to that in terms of the students here that are thinking about, I think a lot of our students now come in rather than trusting us to tell them what to do. They have their own ideas and the things that they want to go do in the world. And they're eager and hungry to go think about startup opportunities when they graduate. What's the right mix between, this is back to kind of the fundamentals versus, should they go kind of hone their craft in a company for a while before they launch a startup, or just head right into it?
I'm speaking from my own experience, and I feel like honing the skill set is important. When you do a startup, the first step is you have to identify the problem properly. To really understand the problem properly, you have to understand the state of the art and what other people have been doing. Fresh out of school, it's probably fair to say you have relatively little idea. So unless it happens to be Facebook or something, something that's brand new, if you're in semiconductor in a field that's very well established, honing the skills, a few hard years of work is important before you start anything on your own.
Okay, you hear that? Kyle, do you hear that? Okay. First question?
Oh, yes, okay. It is almost surely the case that you've acquired a great deal of skill managing people and in business and things like this, but I doubt that you learned that during your graduate studies, and I would like to hear from you what those skills mean to you. Were they hard to acquire? What is the relative importance of your management prowess relative to your technical prowess now?
That's an interesting question. So coming out of Yale, I was 24 years old. I was asked to manage two 50-year-old technicians when I got to Intel. So that was my management learning experience. It was I liken it to drinking from a fire hose. So it's really a matter of how much you can take rather than how much you have to give. So you learn quickly in that environment. I'm very grateful to Intel. Today, we play in the market. We're a relatively small company. We don't really play in the mainstream in a large scale kind of sense. We try to identify unique opportunities where our technology, our thinking can make a difference. So in that sense, I spend most of my time being the CTO, even though I am also the chairman and CEO. I spend most of the time being the CTO. So the technical understanding in setting the right direction is what I focus the most. But of course, you still have a couple hundred people. You still have to manage them. You still have to do compliance work and raise money and all that. That's all necessary. But in my case, technical expertise is still the most important.
Other questions?
Hi, thank you for your presentation. Sometimes within a company, I've seen conflicting directional goals between the technological, like research engineers versus what the market demands are. Would you say in the semiconductor industry, those two are rather aligned more than conflicting, where the better the technology is, it's just readily accepted by the market?
That's not true. So it's true in one sense that everybody is pursuing more advanced technology. So if you're able to go to 1.5 angstrom or something, you obviously have something to offer. So in that sense, it's correct. But still, it's a market. So product definition, market definition, finding the right customers, that's still how you make money. So even when you have the most advanced technology, if you don't have the right product definition, you will still fail. So it's still the same in that sense. It's the same as every other industry.
Thank you so much for the talk. I wanted to ask about in your experience, because very often when we come to these talks, I think we get very excited about some applications, but there's always still a little bit of a gap between maybe our field of expertise in the PhD and the specific knowledge that you need for this field, right? So I wanted to know, in your experience, did you have to deal with this gap between, let's say, what you worked on, what you researched on during your PhD and what you ended up doing later? And how far away from what you were trained on specifically did you wander off during your career? Thank you.
That's another good question. What I actually do today is pretty far from what I studied, what I did for my PhD. But the fundamentals are the same. The fundamentals in two different sense. One is from a technical point of view. What I studied was device physics. obviously device physics is the fundamental building block of semiconductor technology. Right? So understanding device physics, understanding how the pieces come together is a key fundamental skill set for understanding semiconductor technology. The second is the ability to think about the problem, any problem, or be it money problem or people problem. That skill set is the same, regardless of what you do. So I think in the PhD program, the most important thing you learn is actually the second part, how you look at the problem and think about it systematically and address it systematically, not necessarily the first part. So you could be a history major and start a company and make a lot of money, and obviously it doesn't have a lot to do with history, but it's still the problem-solving skills that you learn in your PhD program that matters.
Yeah, hello. Okay. Yeah, thank you for the talk. Amazing presentation. What would you say? I think one of the things that are hard for PhD students and for students in general is that when we see a new idea like your VHM, everything is super exciting, and one of the things that is hard to know without the knowledge of the field or the precise technical knowledge associated is why isn't it already the chips we use in big data centers? What are the challenges linked to that approach? I think in terms of 3D architectures and leveraging the third dimension in chips, I feel like this is has been amazing idea for a while. This is the first time I hear it more in terms of purely a memory point of view and less in terms of just trying to stack transistors. But what would you say are the big challenges that this area of the technology faces?
Yeah, that's another good question. So like any other technology, in order for a new technology to be adopted on a large scale, you need an ecosystem. Right? You need not only customers who are willing to adopt it, but also all the manufacturing partners who have the capacity and willingness and the economics to make it happen. That usually takes a while. So maybe an immediately close example is HBM. HBM started in something like 2012. It was something actually, this is maybe an interesting thing to share. HBM was started not for AI. There was no AI in 2012. Right? It was started for graphics. And it took them many, many years before they had anything. I think maybe around 2015 or so, 16 or so, they had some GPUs that had HBM. And when AI came along, they were very lucky because they were right there and they had the right technology for AI. So even for HBM, which was very well recognized in graphics field as the next generation technology, it took them many years. So it does take time, mainly because of the ecosystem development.
Professor Han.
Yeah, thank you, Wen. You and C.C. Wei, you are I would say two of the more or the most prominent alumni from the micro area of EE, so it's wonderful. And both of you are doing, let's say, hardware. I just call it hardware or semiconductors. And you also involved in, let's say, Taiwan, U.S., China, and whether travel, business, all these connections. And given the complicated situation right now or for the past 5 years or in the foreseeable future, in terms of the hardware technology, what would be your prediction about the opportunities in the U.S.? I think we have a lot of undergrads, and if we encourage them to pursue hardware, semiconductors, and if they want to stay in the U.S., what would be your recommendation or your outlook regarding the opportunities of hardware, semiconductors in the U.S.?
hardware semiconductor actually is very, very big in the US. Most of the largest semiconductor companies are in the US, Qualcomm, Broadcom, those guys. Right? So the trouble with those guys is they all manufacture in Asia. Right? So, but in terms of manufacturing infrastructure, there's clearly a drive to pull them back, to bring them back into the US. It's hard. It will take many years, if not decades, to rebuild the ecosystem that we need. But there is, I think in terms of national policy, there's clearly a very large drive to make that happen. So I think, in terms of hardware, there are plenty of opportunities. Obviously the world is still kind of flat. So we don't have to necessarily think of opportunities in the US. Nobody says you couldn't go to Taiwan and work for a few years and bring some of the expertise back. Right? Just like I came from China and did something here and went back to Taiwan, or the free flow of people is still doable.
Another question. Can I get the mic back? Thank you so much. So maybe this is a follow-on question to Professor Hans. The current climate for research in universities is to say the least, somewhat vexed given, modern political developments. It's led me to consider the question of the sort of the pipeline problem for technology as a particular justification for maintaining the strength of research universities. Do you share that perspective? And should we be calling on our industry community and leaders in industry to speak up for the importance and prominence of excellent PhD programs like the one you came from, and other institutions for engineering excellence and research?
Yeah, I definitely agree with that assertion. Industry needs universities to provide the talent, and the universities need industry to support them. So this is part of the challenge in the US today is, there are fewer and fewer, maybe I shouldn't say fewer, but the emphasis on technology, engineering is less in our universities. Whereas in Asia, that's the most important thing. So as the industry shifts back, or the manufacturing shifts back to the US to some degree, or at least as we try to do that, I think it will become more important, and we do need the industry partners, or even the policymakers, to really think about that.
Mm-hmm. Good. That was the right answer. Thank you. Well, are there any other questions? Otherwise, I'd love to thank Wen again for joining us here, and thank SciCity for this amazing space where we love to have these kind of events. Please stick around and come up and say hi and enjoy some refreshments. Thanks again for coming.
Thank you.